Okay, so I want to talk about centripetal forces now. If we remember Newton's second law, we can remember that net forces can be described as a mass times acceleration. Well, we do the same type of thing for centripetal force. We say that centripetal force is equal to mass times centripetal acceleration. And remember this word centripetal, it means center seeking. So both the acceleration and the force that keep things in circular motion are directed towards the center of the circle. When we use this formula, what it's telling us is how big of a force is needed to keep something traveling in circular motion. That's what this formula tells us. Um, it's usually, well, it's always something else that's actually providing this force. Maybe it's gravity, maybe it's friction, maybe it's someone applying a force, but there is a force that makes something travel in circular motion. Otherwise, it wouldn't travel in circular motion. So this example that we have here, making use of mv squared over r, is the magnitude of the centripetal force exerted by the rim of a dragster wheel. So the rim applies a force on this 45 kilogram tire. The tire has a radius of 48 centimeters and is rotating at a speed of 30 meters per second. So how big of a force does this rim apply on the tire to keep it in circular motion? So if we go through and figure out this calculation, 45 kilograms is the mass, the speed 30 meters per second, and then you square it, divide by the radius, and you get a huge force. Okay, that's a huge force, 84,000 newtons. So that's the equivalent to an approximately 8,400 kilogram weight. So there's some huge forces involved in keeping these dragster wheels in circular motions, especially at 30 meters per second, which is fairly fast. Um, and if you look at some of these the high speed footage of these type of things online, you'll see the tire starts to deform, gets misshapen, and it's kind of bald like this because it what ends up happening is it heats up so much it actually helps the traction out. It's kind of cool to look at high speed, but you can take a look at that online. So what we're going to look at is some continued questions about forces that are keeping things in circular motion. One great example is just cornering or turning in a vehicle. If you're making a turn on a vehicle and we can approximate it as circular motion, then we have to realize the only thing that's keeping us in circular motion is force friction. If there's not enough frictional force between the tires and the road, you're not going to be able to stay in circular motion. And that's kind of important, is realizing that just cornering in a vehicle relies on force friction. It controls how you drive on icy or wet roads. So here's an example. Determine the maximum speed that a 1,500 kilogram car can round a curve that has a radius of 40 meters if the coefficient of static friction between the tires and the road is 0.6. So this kind of goes back a little bit to our dynamics unit. We've got a coefficient of friction, but the way it would start is we would say the force centripetal has to equal the force friction. That's kind of the break-even point. If the force centripetal is too big, then it doesn't travel in circular motion. If it's smaller, then it can travel in circular motion, but it's not traveling. The vehicle wouldn't be traveling at its maximum speed, which is what we're looking for. So mv squared over r is the force centripetal. Force friction is mu times m times g. And when you set those two equal to each other, you notice that the mass doesn't even matter. We didn't need to know the mass of the vehicle because it doesn't matter. But we get v squared over r equals mu times g. So v squared is mu times g times r, and you square root that. So 0.6 times 9.81 times 40, all square rooted, and you find out 15 meters per second, which means if you go faster than 15, you're going to go into a skid on that road and not be able to travel in circular motion. So that's part of the reason why they have, when you're driving, you'll notice times they'll have warnings about how fast you can take a corner at. Well, clearly they build it in that people are probably going to go faster. So they design it so that you probably could go faster, but to be safe, you should stay within the recommended speeds of the corners, especially if the road conditions are poor. We're going to talk a little bit about gravitational forces, how they are involved with centripetal forces. But before I do that, I wanted to talk a little bit about um, the connection between speed, period, and frequency and centripetal forces. You'll find that most times you buy tools or motors that are designed to rotate or have a certain speed on them. They're listed as RPM. They don't give you the meters per second rating of a drill, for instance. It's an RPM. And the reason why that is because when something's spinning like this, um, the whole disk has the same frequency, but different spots on the disk have a different speed. So if an object was sitting here, it would have to travel a further distance in the same time as the object at position A. And so the speed of an object sitting at position C would be greater than A, even though the disk itself or the wheel itself is spinning at the same rate. And so we start looking at the same analogy with the Earth, and the Earth spins at about 1,000 kilometers per hour. Well, that's at the equator. Okay, it has to travel all that distance, this whole circumference of the Earth, in 24 hours. Well, as you get closer to the axis in which the Earth rotates, that same distance takes 24 hours. And so as you get closer and closer to the axes at which the Earth spins on, you're actually going to have a slower speed, um, which is part of the reason why actually at the equator, some of your gravitational forces are used up, keeping you on the Earth. And so in a way, you're feeling lighter at the equator. But the issue is that it's not a significant difference in the weight. You don't just go there and go, "Wow, I feel like I lost some mass." No, it's still going to feel pretty close to what our gravitational forces are here. There's going to be a small difference. Well, if we take a look at our formulas for centripetal acceleration, v squared over r, and our formula for v, what they're going to show you is that if you wanted to get an equation for centripetal acceleration that doesn't have speed in it, just frequency and period, you could take this equation and you could square it, because that's what v squared stands for. So 2 pi r, you'd square that, you'd square the period, so you get 2 pi r all squared over radius times t squared. That's just v squared over r. And when you multiply it all out, you get 4 pi squared r squared over rt squared. One of the r's cancel, and so you end up with this formula for centripetal acceleration. And then if you want to include the force centripetal on that, the difference between centripetal acceleration and centripetal force is just multiply by the mass. That's the only difference between centripetal acceleration and centripetal force. And if you take that same equation and you replace, if you remember that 1 over the period, or period, take the reciprocal of the period, you get the frequency. You can find out that in terms of frequency, the acceleration is 4 pi squared r times frequency squared, and the centripetal force is 4 pi squared mass times radius times frequency squared. All these equations are on your formula sheet as well. So here's an example. The compressor blades in a jet engine have a diameter of 42 centimeters and turn at 15,960 revolutions per minute. Determine the magnitude of the acceleration at the tip of each compressor blade. All right, so with this revolutions per minute, we've got to remember to divide by 60 to get revolutions per second. And we find that the frequency is 266 revolutions per second, or 266 hertz. Then we remember, oh yeah, we have a formula. We just talked about it, a formula for acceleration. If we don't know the speed, it's 4 pi squared r times frequency squared. The only thing more we need to do is figure out the radius. Since the diameter is 42, the radius is 21 centimeters or 0.21 meters. So you substitute that for the radius, use the 266 hertz for the frequency, and you find out that you have this huge 5.87 times 10 to the fifth meters per second squared um, acceleration of the um, what is it? Compressor blade in a jet engine. All right. And if we knew the mass of this compressor blade, it looks like it's fairly massive. We could times that acceleration by the mass to find the centripetal force. Some pretty big numbers involved here. Centripetal accelerations are things that are spinning tend to, especially if they're spinning fast, tend to have big accelerations and forces acting on them. Okay, so the next video we'll talk a little bit more about how gravity weighs in with uniform circular motion. We're going to look at carnival rides that spin, go upside down. But all of this stuff applies well to a lot of carnival rides because there's a lot of carnival rides that just spin. And so far we're kind of looking at horizontal, but we're going to look at vertical circular motion and how gravity plays a role in the other video.